We have been building toward this episode for 2 episodes. In episode 1, we understood why hybrid search exists. In episode 2, we built the hybrid search collection and the prefetch query in Python. Today, we take that implementation and make it production. That means wrapping it in a FastAPI service, adding a cross-encoder reranker as a second stage, enabling memory quantization, and adding the observability to know when the reranker is actually changing the ranking. Here's the title claim I want to back up with numbers by the end of this video. Why your RAG pipeline is missing 30% of results. That 30% is the precision improvement from the hybrid retrieval over pure semantic search. But here's what is also true. Hybrid search alone is not the full story. Adding a two-stage reranker closes an additional gap. I will show you a three-way benchmark. Dense only versus hybrid only versus hybrid with reranking. The architecture I'm building today is the pattern I would deploy if a client asks for a production RAG search API. Let's build it. Production retrieval systems at scale follow a two-stage pipeline. Here's why. Stage 1 is retrieval. Cast a wide net, run a hybrid search, dense plus sparse with RRF, and return 20 to 50 candidates. The goal of stage 1 is recall. You want every relevant document to be in a candidate list. Hybrid search is the right tool here. It combines semantic understanding with exact token matching, and Qdrant runs both in one request. Stage 2 is reranking. Sort the candidates precisely, take the top 20 from stage 1 and run them through a cross-encoder reranker. The goal of stage 2 is precision. You want the single most relevant document to be ranked 1. Cross-encoders are more accurate than bi-encoders similarity. They look at the query and each candidate document together, rather than comparing separate embeddings. The latency trade-off is manageable. Stage 1, Qdrant Hybrid Search approximately takes 8 milliseconds P95. Stage 2, cross-encoder reranking on 20 candidates approximately 20 milliseconds. Total approximately 28 milliseconds. Compare that to PG vector at 48 milliseconds P95 with no reranking. We get better accuracy for less latency than the naive baseline. This is the architecture. Two-stage, wide net, then fine sieve. Let us build it. Let us start with the FastAPI service architecture. Here is the service layout. The API has one endpoint, post search. Request body takes a query string, optional filters, and top key. Response returns results with both retrieval score and rerank score. I want both visible in the response so I can observe where the reranker changed the ranking. On the right hand side here, the Pydantic models. The latency fields in the response are not optional. They are how I will know if the system is performing within budget. Let's go inside the episode 3 production rack. In the API models PY, we can see them also. Stage 1, the hybrid retriever. This is the episode 2 code refactored into a class. Here is the retriever class, as you can see on the left hand side. A few things I want to highlight. The method async. FastAPI uses an async event loop, and blocking the loop with synchronous model inference is a production anti-pattern. In a real deployment, I would move the embedding computation to background thread, pull using async IO in executor. For this demo, the models are fast enough on CPU that is fine. The candidate limits is 20 as a default. This is the input to stage 2. If you increase this, reranking takes longer. It's on in the number of candidates. If you decrease it, you risk the correct answer not making into the candidate list at all. 20 is the right starting point. Increase it if you see recall 20 below 80%. The build filter helper converts the flat filters to dictionary, a Qdrant filter object with must conditions. I am keeping this simple. In production, you would want a richer filtered DSL. In the code, in the rows, we can see the search row here. Let's go inside the retrieval, hybrid retrieval. Let's see the code here also in Visual Studio. The build filter is here. The retrieve is here. So it's calculating the dense vector here, sparse vector here, and it builds the Qdrant filter with this build filter from the filters, which is a dictionary. And we will return the points and elapsed milliseconds. That's it. Stage 2, the cross-encoder reranker. Here is the reranker. Why is the cross-encoder more accurate than a bi-encoder? A bi-encoder embeds the query and the document separately and compares the resulting vectors. The query and document never see each other during encoding. All cross-document reasoning happens at the comparison step. A cross-encoder takes the query and document as a concatenated input and processes them together. Every attention head in the cross-encoder can attend to both the query tokens and the document tokens simultaneously. This gives the model significantly more information about the relevance relationship, at the cost of being much slower. You cannot use a cross-encoder to search a million documents directly. It would take minutes. That is why stage 1 exists. Fast candidate retrieval, then precise reranking on a small candidate set. The model I am using is the cross-encoder MS Macro Mini LML6v2, something like that. It's trained on the MS Macro passage ranking dataset. It is standard production-ready cross-encoder for RAG reranking. Small enough to run on CPU, accurate enough to do matter. One thing to watch: the cross-encoder scores are raw logics, not probabilities. They are compared within a batch. You can sort by them, but not between batches. Do not interpret the absolute value as a confidence percentage. Okay? Now the pipeline that orchestrates both stages. Here is the pipeline that ties it together. Yep, in the Visual Studio Code, you can see the retrieval pipeline. Yep, now. So, the two latency measurements are the key observability feature here. When you see retrieval MS here above 20 millisecond, check Qdrant load and memory. When you see rerank MS above 50 millisecond here, you have too many candidates. Reduce the candidate limit or upgrade to a GPU. Both the RRF score and the rerank score are in the response. This lets you log both and measure how often the reranker changed the ranking. The logging is what tells you whether the reranker is actually adding value for your specific dataset. Let me show you the latency numbers and quantization settings. Here is the full latency picture. Qdrant Hybrid Search 8 millisecond P95 at 1 million vectors. This is the stage 1 cost. It does not change significantly whether you have 100 key or 5 million vectors, because H and SW traversal is logarithmic in collection size. CrossEncoder reranking on 20 candidates, approximately 20 milliseconds on a CPU. If you add GPU inference, this drops under 5 milliseconds. The MS Macro Mini LM-L6v2 model runs in about 20 milliseconds on a modern CPU core for 20 candidate pairs. Total 28 milliseconds. Compare this to PG vector at 48 milliseconds with pure dense search and no reranking. We are getting both higher precision and lower total latency. Now quantization. Qdrant ScalarQuantization converts 32-bit float vectors to 8-bit integers. This reduces memory by 4x with less than 5% accuracy loss on most benchmarks. For a collection of 1,384 dimensional vectors, that is roughly 1.4 GB of dense vector storage, reduced to just 350 megabytes. Look at here, quantized vector stays in memory. This always RAM equals true keeps the quantized vectors in memory even if the original vectors are on disk. Quantil 0.99 means we clip the top 1% of extreme values before quantizing. This protects accuracy on outlier vectors. Now the observability layer. How to know when the reranker is actually doing something? The reranker is only valuable if it changes the ranking in ways that improve precision. How do you know if it is? Log the rank changes. Log this for every query in production for the first 2 weeks. If the reranker is changing fewer than 10% of queries, your hybrid search is already accurate enough. You may not need reranking for your specific dataset. If it is changing 50% or more, reranker is adding a real value. This is how you make architectural decisions based on evidence, not benchmarks from someone else's dataset. The fallback. What happens when both retrieval stages return 0 results? Every production pipeline needs a fallback to the 0 candidate case. This happens when a filter is too restrictive, or the query contains no terms in the vocabulary, or the collection is empty for a given tenant. 2 fallback levels. First, retry the query without filters. This handles the case where the filter was too restrictive. A category filter that has no products in the current collection, look when this happens. It is a data quality signal. Second, if even the filterless query returns nothing, return an empty result set with an explicit fallback field. Do not silently return empty. The calling application needs to know it received a genuine empty result rather than error. Do not attempt hallucinated fallbacks like let me try border query. That is production decision, not a retrieval decision. The retrieval service returns what is there. The application decides what to show to user. Now the benchmark. The three-way comparison that closes this series. I have 10 labeled test queries in the evaluation dataset. Each query has a ground truth, the correct document ID that should appear at rank 1. 3 strategies: dense only, hybrid, which means dense plus sparse plus RRF, and hybrid with cross-encoder reranking that I explained just now. Here are the precision 1 numbers. Dense only, 40%, 4 of 10 queries return the correct answer at the rank 1. Hybrid, no reranker, is 70%, 7 of 10, and hybrid reranker is 90%, 9 of 10. This is the story in 3 numbers. Hybrid search closes the majority of the gap. The reranker closes most of what remains. The one query that fails is paraphrase style query, where neither the M25 nor the cross-encoder has seen exact terminology. A GNU coverage gap that would require adding the document or expanding the embedding with domain-specific fine-tuning. Now precision 5. Does the correct answer appear anywhere in top 5? Dense only, 70%, hybrid 90%, hybrid plus reranker is 100%, as you can see here. At recall 5, all 3 strategies are comparable. The correct answer is somewhere in the top 5. The difference is entirely about ranking precision. Getting the right answer to rank 1, which is what matters when you use the top result to generate an LLM response. This is the production argument for two-stage retrieval. Retrieval 5 is not the metric that matters. Precision 1 is, because your LLM reads the top result. Let's went back to Visual Studio and let's run the benchmark. I made a typo. I fixed my typo. Let us run it. It loading the weights. Now the query is coming. Yep. Hybrid is improved hit 1 from 75 to 100%. Reranker did not degrade and stayed at 1. That was the benchmark. Let me wrap up the series. 3 episodes. Here is what we built. Episode 1. The architectural understanding. The two failure modes. BM25 mechanics, HNSW, and RRF versus DBSF fusion, and the production benchmark numbers. Episode 2. The Python implementation, Qdrant collection with named vector spaces, fast embedded BM25 without Elasticsearch, the prefetch API running both searches in one request, payload filtering, IDF modifier, and a side-by-side precision comparison. This episode 3, production engineering, FastAPI service, CrossEncoder reranking as a second stage, ScalarQuantization to cut memory by 4x, observability logging for rank changes, fallback strategy for 0 candidates, and a 3-way benchmark showing dense only, hybrid, and hybrid with reranking. The GitHub repo is Qdrant Hybrid Search Lab, and 3 branches, episode 1, 2, and 3, that it's in the description. Clone it, run it, measure it against your own datasets. The architecture I showed you in the series, hybrid retrieval plus cross-encoder reranking, is in the production pattern that appears in the job requirements for senior RAG engineering roles, not PG vector with cosine similarity. This one. If you are evaluating a vector database for production AI system, this is where to start. If you want help designing the retrieval layer for a production system, my Upwork profile is in the description. You can work with me. Subscribe for more production AI engineering content. Links, all 3 episodes and the GitHub repo are below. Thank you guys. See you next time.